Hi, in this video lecture, now we will start with standard hydrogen electrode. In standard hydrogen electrode, standard means standard refers to here standard conditions of temperature, pressure and concentration of solution. Right, so here standard hydrogen electrode. Here standard stands for pressure 1 atmosphere 1 bar, right, and temperature 25 degrees Celsius, which is 298 Kelvin, and concentration is 1 molar, right. Now let's understand what is hydrogen electrode. Since we have studied in previous where we studied the working of galvanic cell or electrochemical cell, it consists of two half cells, right, which are electrodes. This is zinc electrode and this is copper electrode, and these electrodes have metal rods in contact with its own ions. Here copper is in contact with its own ions, right. Here zinc rod is in contact with its own ions, right. So here, since these are metal rods, right, which are in contact with its own ions, we call these as metal electrodes, right. So now here we have hydrogen electrode, and we know hydrogen is a gas. So when we say hydrogen electrode, that means hydrogen gas is in contact with its own ions, right, and it forms hydrogen electrode and is a gas electrode, right. That means hydrogen gas is in contact with its own ions, which are hydrogen ions, right. These are hydrogen ions, right, and this is a gas electrode. So we said hydrogen gas is in contact with its own ions, right. So how can we bring hydrogen gas in contact with its own ions? We will understand it from this diagram, from the construction of standard hydrogen electrode. It's a very simple diagram, right. It consists of this vessel that has HCl, that has solution of HCl in it, right, and we know HCl will ionize into hydrogen ions and chloride ions. So this solution contains hydrogen ions, right. So we have now hydrogen ions in this solution. Now let's see how can we bring hydrogen gas in contact with these ions. The one that is shown in red color, this is a glass vessel or a glass jacket, we call it a glass jacket, right, that has a platinum wire inside it, and this platinum wire is connected to the platinum plate, right, and which has a platinum black, right, on its surface, platinum black coated on its surface, right. So I repeat, here we have a glass jacket that has inside it a platinum wire that has a platinum plate coated with platinum black, right, and this has an inlet also. This glass jacket has an inlet. Through this inlet we pass hydrogen gas inside this glass jacket that will get absorbed on this platinum plate, right. By adsorption we mean that hydrogen would be found on the surface of this platinum plate, right. And if you remember, we have studied in previous classes when we have gone through chapter hydrogen, that hydrogen has a property to get adsorbed on the surface of metals like platinum and palladium, and this property is also called as occlusion of hydrogen, if you remember. So we have made use of the property of hydrogen called adsorption or occlusion, due to which it gets adsorbed on the surface of the platinum metal, right. So since hydrogen gas is on the surface of this platinum plate, and this platinum plate is immersed in this solution of HCl, right, which contains hydrogen ions. So this is how hydrogen gas, which is adsorbed on this platinum plate, is in contact with hydrogen ions, which is in this solution of HCl, right? So we have made use of the property of hydrogen called adsorption. So we say hydrogen is adsorbed on platinum plate, which is immersed in HCl solution that contains hydrogen ions, right? So now hydrogen gas is in contact with its own ions, right? So this forms a gas electrode, standard hydrogen electrode. Now the other thing is, we have hydrogen ions inside this, and this is the platinum plate that is coated with platinum black and has hydrogen gas adsorbed on it, right? This is hydrogen gas adsorbed on it. So here two things can happen, right? Either this hydrogen will form hydrogen ions, right? That is, oxidation of hydrogen takes place to form hydrogen ions, or this hydrogen ions will form hydrogen gas, right? So reduction of hydrogen ions will take place to form hydrogen gas, right? So we write these as hydrogen will lose 2 electrons to form 2 hydrogen ions. This is your oxidation reaction. So, or the other reaction is where hydrogen ions in the solution will gain 2 electrons. 2 hydrogen ions will gain 2 electrons to form hydrogen gas. This is your reduction reaction, right? So this is oxidation occurs, we know, at anode, and this occurs at cathode, right? So we say she, that is standard hydrogen electrode, act as anode as well as cathode, right? So this is clear how it can act as anode as well as cathode, because it can undergo oxidation as well as reduction, anode and cathode, right? So this can act as anode as well as cathode. And the most important use of standard hydrogen electrode is to determine the electrode potential of other electrodes, right? It is used to determine the electrode potential of other electrodes, right? And the other most important thing is its electrode potential. The electrode potential of SHE is 0 volt, right? The electrode potential of standard hydrogen electrode is arbitrarily chosen as 0 volt, right? And it is used to determine the electrode potential of other electrodes. We'll see how. Since if we have hydrogen electrode, since if we have zinc electrode, only zinc, if we want to determine if we want to find the electrode potential of zinc electrode, right? So zinc electrode, what we do is we couple zinc electrode with this standard hydrogen electrode to form an electrochemical cell, right? And determine the potential difference or EMF of the electrochemical cell that results from the coupling of zinc electrode and standard hydrogen electrode. And we know that the electrode potential of standard hydrogen electrode is 0, right? So whatever is the EMF of the entire cell, right, EMF of the cell, is the electrode potential of the other electrode, which is zinc, right? I'll just try to make you understand. Since we know that EMF of electrochemical cell is ER minus EL, right? And these are, and we know that ER and EL are reduction potentials as per IUPAC convention, right? So suppose we want to determine the standard electrode potential of zinc electrode, right? So what we do is, since zinc electrode, suppose we have zinc electrode and which has zinc electrode and zinc sulfate solution inside it. This is zinc electrode, right? Zinc rod. And if we want to determine the standard electrode potential of zinc electrode, right? And standard electrode potential, that means the electrode potential of any electrode, say zinc electrode, is due to the oxidation or reduction reaction that takes place at the electrode, right? If you recall what we have done in the previous lecture in electrode potential of electrodes, the electrical double layer that gets formed at the interface of this metal rod was as a result of oxidation reaction or the reduction reaction in case of copper rod, right? So if we have single electrode, right? Single electrode, at single electrode, oxidation or reduction potential is not possible, right? If we have this single electrode, it would not be able to lose, say, since zinc electrode is losing electron here, which is gained by copper electrode, right? There is a transfer of electron. Due to this transfer of electron, the spontaneous reaction is taking place, right? And due to this spontaneous reaction, redox reaction, the electrode potentials developed in both the half cells, right? Now if we have single electrode, this zinc electrode, it would not, like here it's losing an electron. In this case it won't lose any electron because the oxidation reaction cannot take place in a single half cell, right? This is a single half cell, right? So it would not lose any electron. There would be no transfer of electron because there is no one to gain this electron, right? Because we have to have some electrode, that is, we have to have the other half cell to complete this electrochemical cell, so that the electron that is lost by this electrode, right, which is under investigation, for which we are trying to find electrode potential, the electron lost by this electrode should be gained by some other electrode, otherwise it will not lose any electron. So no loss of electron means no oxidation reaction. No oxidation reaction means no electrode potential. So it won't create any electrode potential. So there is no question of finding the electrode potential of this electrode. So what we do need is, if we want to find the electrode potential of this single electrode, we have to have a standard electrode or a reference electrode, right, using which we can complete this transfer of electron and determine the electrode potential of this electrode. I repeat, in order to determine the electrode potential of this single electrode, we have to have some reference electrode or the standard electrode, right, using which we can complete this transfer of electron, that is redox reaction, so that when this electrode, reference electrode, is in place, this electrode can lose electron. If it is zinc, this electrode can lose electron, which would be gained by this reference electrode, so as to complete this redox reaction, right? When there is transfer of electron, so some electrode potential would be developed here, and here also electrode potential will get developed, right? So due to the electrode potentials that get develop, we can calculate the value of electrode potential of this electrode. And since we know, if we take standard hydrogen electrode as the reference electrode, the electrode potential of SHE is 0 volt, right? So when we determine the EMF of this cell which is formed as a result of coupling of electrode under investigation, that is for which we are trying to find the electrode potential, with standard hydrogen electrode. The EMF of this cell would be the electrode potential of this electrode only, right? Like if this is the EMF or the potential difference of this cell, which is ER minus EL, right? ER is the, say, reduction is taking place at hydrogen electrode, because we know that hydrogen electrode can act as cathode as well as anode. So let's suppose its reduction is taking place here. So we know that since these are reduction potentials, so reduction potential for cathode, this is the electrode potential for cathode, this is the electrode potential for anode, and we know that electrode potential of cathode, which is nothing but a reduction potential as per IUPAC, is a positive value, and electrode potential of anode, that is the left one, which is zinc, would be negative. It would be a negative value, right? So say experimentally it's been determined that the electrode potential of this cell when zinc is coupled with SHE is 0.76 volt, right? And ER is reduction potential of this, the one that is in the right, that is SHE, right? So we know that standard reduction potential of SHE is 0, right? Minus, and this is what? This is the reduction potential of anode, right? And we know that the reduction potential of anode is a negative value, right? Which is, say it's minus x, say it's minus x, for which we need to find the value of this EL, the electrode potential of this zinc, right? And since we are taking the reduction potentials as per IUPAC convention, so the value of EL would be negative, right? So it's negative. So I said this is the value of EMF of this cell. So we will, using voltmeter, we will calculate the EMF of this cell, or using potentiometer we will find the EMF of the cell, right? Whatever is the reading of the potentiometer, we will mark it, we will enter the value of potentiometer here, which is 0.76 volt, right? So this is 0.76 volt, this is for SHE we know is 0, and this is X. So X, that is electrode potential of this zinc electrode, is 0.76, right? So this proves what I said at the beginning, that when we couple SHE with the other electrode for which we are trying to find the electrode potential, right, the EMF of the cell formed would be the electrode potential of the other electrode for which we are trying to find the electrode potential, right? So this is X would be 0.76, right? So I hope this is clear to you. This is the most important use of SHE, that it is used to determine the electrode potential of other electrodes, right? And its electrode potential is 0, right? So whatever is the reading